Great. All right, so move on next lecture, Vladimir.
Good morning. So I assume some of you have been in my previous lecture on Wednesday. I will repeat this, but also I have a feeling that you already know everything that I see there. Oops. Why it doesn't work? Somehow something doesn't switch. It was switching a moment ago.
Oh, sorry, let me make sure it's quick on the screen. Okay. Does that do it?
No.
Where's the other one? Try this one.
Somehow it's stuck.
Yeah, did you?
Yeah.
Okay.
So
The pointer doesn't work either.
I have pointer. I have my own pointer.
Yeah.
The pointer is not the problem, but I do need to switch to go along. Otherwise, we'll steer the whole hour at this.
Is that you or me? Can't figure out which. It's probably have two. We have no.
Maybe it ran out of battery because it was working like a moment ago.
You know which one it is? Yeah, this one.
That's working. Yeah. Okay. So we're trying to derive this BF-Kyle Hamiltonian, right? We was talking. So this is our diagram. No, okay. So this is a photon, virtual photon coming from electron. It turns into this couple of virtual quark contact quark. This is valence quark exchange gluons. So this is layer of gluons, or I don't know, chain. I'll say call it chain. And then these gluons interact, and we want to derive a Hamiltonian of interaction. So roughly speaking, the history was like this. BF-Kyle, this it's also running out. Okay, so maybe death of the batteries. Because of the batteries. So BF-Kyle, they try to sum up all of these diagrams. And then it's kind of difficult, so they get a linear integral equation for the sum. And the Fourier transform of the integral equation is that Hamiltonian, which I showed several times. So that the history, and from time to time, I'll be using Z. Z is a coordinate in the plane perpendicular to this momentum, right? This is TMZ, but it's not momentum, it's coordinate. All right. So there are several different ways to derive this BF-Kyle Hamiltonian. One of the ways, the one which I suggest right now, we can start with three diagrams. Three diagrams cannot be very difficult, right? There's no integration, so just write them down. On the other hand, Witten with co-authors, he wrote a nice paper, kind of a recursion relation. No, this different. So Witten, Kachara, and others, Britta Feng, they wrote some kind of recursion relation for three diagrams in Young-Mills. So let's have a look. So this is just some tree diagram. Next frame has a picture, and then I cut it, and then I put one of a p squared, the cut place, and this is left side of the diagram and the right side of the. That's a picture. So this is three diagrams. There's no loops, no integration, and then I cut it into pieces. One subpiece, subdiagram, another subdiagram, 1 divided by p squared, and I sum up with this place of the. It's nice. Of course, it's not very difficult because there's no loops, no integration. On the other hand, it's useful for us. So next thing to do, before even calculating radiative corrections, we want to express these diagrams, the three diagrams, in terms of z, this coordinates in the plane perpendicular. I write it down, and well, this momentum, this is the typo, this should be this q momentum, and z, the plane perpendicular. So I want to write these three diagrams in terms of z. I do that, and then I get disappointment because there's analytical piece and non-analytical piece. I like analytical function. I dislike some kind of z bar together. So, and then BF-Kyle, they discovered a trick, rigidization. So one can take into account radiative correction in a clever way. One can take into account one particle exchange in the T channel. And then this non-analytical piece disappear and everything become analytical in Z, which is nice. And that was the way, this is their Hamiltonian, BF Kyle Hamiltonian. This is Z, well, this is actually P is momentum, TMZ. And Z is the coordinate. I showed it last time ago, and we have this chain with periodic boundary condition. I mean, of course, this is like one of the leading ideas in the derivation, because derivation of BF Kyle Hamiltonian is difficult. But it's fully presented in this long paper by Ronald Kirchner, so you can click on this because PDF file in the possession of the organizing committee. This all details, but this is long stuff. And then Kirchner here starts with this BF Kyle, and in their annotation, write my Bethe-Ansatz equations. Remember Bethe-Ansatz, we have this machinery, valence bond, auxiliary dimension, L operator. So here Kirchner writes this L operator in terms of these Z variables, but maybe this is too technical, so let me skip it. And then this L operator has R matrix. This is R matrix which intertwine two L operators in two different quantum spaces. That's exactly the one which we saw on Wednesday. On Wednesday for latest nonlinear Schrödinger. Hamiltonian is also, this is size logarithmic derivative of gamma function. So this is looks good to me. Okay, so once again, this is the same Hamiltonian, but now we don't want to write this BF Kyle Hamiltonian in terms of Z and Z derivative. I mean, BF Kyle, Lipatov, they notice that the whole Hamiltonian can be rewritten in terms of this S plus, S minus, S Z, which is just some combination, Z derivative and Z, but all three of them form SU2 algebra. So the commutation relations are given in terms of SU2 algebra, and then Hamiltonian and R matrix can be written only in terms of the generators. And that's R matrix. Hamiltonian also depends on this. So J is quantum operator, which is solution of this quadratic equation, but S is one of those, right? So I take three of them, make a vector, three-dimensional vector, and take this three-dimensional vector and another three-dimensional vector, the nearest neighbors, K will be G plus 1, and make like XX plus YY plus ZZ. But then in this equation, everything commutes, so I can use Viet formula to solve it and plug it in. So it looks horrible so far. This is just what I said. So this is my machinery of the Wednesday. So this is in Bethe-Ansatz we call it trace identities. So Hamiltonian, this is BF Kyle Hamiltonian, this main stuff. And this is logarithmic derivative of R matrix, means that all the machinery of Bethe-Ansatz works. Now, this is just repetition of Wednesday transfer matrix. Maybe just skip this. Let's see what came out. This L operator, you also saw this on Wednesday, this latest nonlinear Schrödinger. So the idea is the following. BF Kyle, they express their Hamiltonian in terms of S plus, S minus, SZ. On the other hand, I have my Heisenberg chain with negative spin on latest nonlinear Schrödinger, which also is the same S. They have the same commutation relation, or they act in a different space. So I just change the space, and then I care only a commutation relation. So BF Kyle I map to latest nonlinear Schrödinger equation because everything what matters here is commutation relation between these operators. So instead of Z and derivative with respect to Z, I take a set of harmonic oscillators and take representation of the Hamiltonian in this set of harmonic oscillators, which I also can call lattice Bose field, right? Bose field on the lattice is this is the set of harmonic oscillators. So all of this machinery, which I explained on Wednesday, works. This is algebraic Bethe-Ansatz, which also, remember, we have this ferromagnetic state, the omega ferromagnetic state. This is operators, creation operator, which create spin waves, right? Color spin waves. Color waves go through the gluons. This is, and they're intelligently, we can construct them in such a way that they are eigenvalues of the Hamiltonian of BF Kyle. So this is traveling color waves. Okay. So Bethe-Ansatz, usually if you take a book or, I don't know, paper on Bethe-Ansatz, usually there is some calculation and the main results in Bethe equations. Bethe equation written for lambdas. Lambdas are rapidities of those waves, of the color waves which go through. They have some kind of momentum along the chain. And the lambdas are set of individual momenta of this different colorway. So I'm supposed to solve this. This is system of equation. K runs through all of the gluons. This is number of the lattice site, number of the gluon. And then this is number of the waves. So I have several traveling waves, they scatter on one another. So I'm supposed to solve the system equation, plug into this expression. This will give me energies. So BF Kyle Hamiltonian. Hamiltonian has energy, ground state energy, excited states. So all of this in the end come from these equations. What?
Sorry, I sort of lost my. No, I have. So are we still in the picture where we've gotten rid of all loops by replacing it with something?
No. Right now there's loops. So what I'm trying to, the beginning was kind of pedagogical, so I can start real easy because I mean 3 diagrams. I mean we can handle this, but then we can start taking the loops into account by this clever way, killing and non-analytical parts. And then we proceed with the loops. There's a lot of loops here. So anyway, this is energy levels of BF-KL Hamiltonian. Okay, so eventually we shall solve them. We shall find ground state energy. The Hamiltonian has some configuration of the traveling waves around, so which is the lowest state energy. And there's also excited states. And this is one-dimensional. I mean, the loop, this quark anti-quark pair. I mean, we call it color singlet dipole. It's one-dimensional. So there is Pauli principle in this beta ansatz, meaning that all lambdas has to be different from one another. This is like specific for one-dimensional kinematics. One-dimensional interacting bosons, if they interact with generic potential, usually this Pauli principle in the momentum space, meaning that eigenvectors also have to have different momenta. So momentas cannot coincide. So all of them are different. And then I'm supposed to solve, plug, and then ground state energy, excited state. So, but the ground state energy, maybe it's the right picture. It will ground state energy, ground state will look like a Fermi sphere. So this is energy of the traveling colorway. And then its momentum, which is lambda. And then I have dispersion curve, dependence of energy on momentum of the traveling color wave. And then there is a state of these waves inside of the Fermi sphere, which is filled in. And there is also something out, zero temperature. But then, among other things, I have this slope, energy versus momentum, which is velocity. So there's like velocity of sound in this media of the waves. And it will reappear later. So the ground state, excited states, and there will be some velocity. I mean, later I will describe everything by conformal field theory. In conformal field theory, usually I have the velocity of light. So I have to substitute something instead of velocity of light to this V. Okay, this is still, all right. So I have my equations, the equations for lambdas. And then I'm supposed to solve them. And we're supposed to go to thermodynamic limit. Thermodynamic limit means many gluons. Thermodynamic limit, like a limit of large volume, many gluons. So far, I just, in beta ansatz, this is standard thing. In beta ansatz, I write beta equations. Next step I do, I go to thermodynamic limit. So means this L goes to infinity. So the ground state energy proportion to the volume, as it should be normally, I expect that's from 19th century, is proportional with some coefficient. And that is a correction, 1/L correction. This is the correction in the limit of large N and L, both N and infinity. Correction is important because if I want to describe this by CFT, then the central charge will stay here. And then this will be our way to calculate central charge of conformal field theory, which describe the FKL. So this is like we're getting to some result.
Excuse me?
Yeah, what?
So in that plot, how do you see that the dispersion relation is quadratic?
It's not quadratic. It's some transcendental function. It's not elementary, even elementary function. Not quadratic.
But it was 1/λ L squared.
It was the sum of this stuff, but there is many terms, and also there is also Pauli principle. Oh well, let me. This is a very good question. Yeah. So first of all, eventually there will be. many of these terms. On top of this is the Pauli principle, meaning that if I consider a hole, let's say in the term C, I kick one out, all others start moving because in here they all interact. So one lambda is out, all others shift a little bit, and then I have to sum it up, which is integral actually in this thermodynamic limit turns into integral. So it's Bayer formula is quadratic, but when I take into account all the quantum corrections, some transcendental curve, we know this, but I've given it implicitly in terms of solution of linear integral equations. This is standard for pure answers. This always happens.
So in the next slide.
Next slide.
Next again.
Yeah.
Yeah. So the correction pi over 6 d times, it looks very similar to the Lushel correction which appears in, for instance, strings.
Yeah. But both of them can be described by control field series. So I just blame CFT.
Just a relation.
Yeah, but this will disappear soon. So this was just the method to calculate central charge of CFT. It is. That short answer is yes. So I proceed. Yeah, proceed. Okay. So let me tell you. So eventually I will compare this to CFT, to control field theory. As I said, central charge should stay here, and then nothing stays here. So central charge is equal to 1. That will be, which often happens in better ansatz solve, almost not universal, but often. Right. So this was so far for better ansatz. But what I want to do now, I want to apply ideas of quantum information to this BF-Kyle. So I want to study the spread of information along the chain. But first of all, what's the measure of information? So in here, before World War II, quantum mechanics was designed, and then people come up with some measure of information. So by now, so we're changing the gears right now. It's not better ansatz anymore. It's just information. So to completely forget everything what I said before that and this new stuff. So what I want to do right now in this slide, this is I want to compare classical random variable to quantum operator. Classical random variable like a die, right? A loaded die. So I throw it, and there's 6 possible outcomes with different probabilities. When I look at it, I gain some information. So how much information I gain? This is the entropy of this random variable. So random variable has some outcomes with different probabilities. So the entropy of the classical random variable. It's not a die, but a bit. I mean, there's 2 outcomes, 0 and 1, and this will be log 2, and then this is a bit of computer, which we usually use. Anyway, so in classical, for classical random variable, there's a theorem. So assume the total entropy is 0. Then one can prove there is no entropy in any subsystem. So the total entropy is 0. Then I cut out some of these x's, not all of them. Still entropy will be 0 for any subsystem. Not so in quantum case. It can so happen that the total entropy is positive, but there is entropy subsystem. So a famous example, it was 1935. Famous example is a singlet made out of 2 spin 1/2, right? So this minus this. Total is a pure state, so entropy is 0. But each spin, actually, each individual spin in the maximally mixed state, which is log 2. So entropy of subsystem is a measure of entanglement. That's what the one which is very popular, and we'll use it here. Okay. So we proceed. We want to study dynamics of entropy. Dynamics of entropy was started in 19th century. In 19th century, people knew classical entropy, right? Classical entropy, dynamics of classical entropy was studied. In Wikipedia, there's an article called Entropy Production. And the main hero is Rudolf Clausius. The kind of gloomy guy with a beard. His picture isn't there. So he was the guy, everybody knows that entropy increased with time, right? But who proves this? Nobody knows. This was this guy. This guy wrote many differential equations, time dependence for differential equation of entropy. And looking at this equation, he proved that the time derivative of entropy is always positive. So we shall study, well, now I changed mentality to better ansatz mentality. So now I want to have questions. This is popular subject in beta ansatz. So this is my spin chain, which is like ladder of gluons. And then there was an incoming photon. So by now, I said that normally this chain wants to stay at ground state and the rest, But then the photon can be considered as some kind of a quench, some local explosion, some local disturbance. And then this local disturbance send a wave along the chain. And the wave will be subject to our attention. This is entropy spread. So entropy spread will go along the chain from this virtual. So something like this, in classical case, it can be compared to small explosion. In the atmosphere, I throw like hand grenade or small explosion. And then the waves start coming. And the wave actually has a front of the wave. Inside of the front, the density of the entropy change. So anyway, in one dimension, one space dimension, entropy is linear function of time. In the classical case, T is temperature, C is my central charge was equal to 1. In classical case. On the other hand, in quantum case, it will be logarithmic, but there is a huge derivation. I don't know. I still have half an hour, so let's go through derivation. I did everything what I told you was without derivation, and you know conformal field theory. So let's use conformal field theory to show that in classical case it was linear, right? But in quantum it's logarithmic in time. We'd use conformal field theory for this. Okay, so so at zero temperature, entropy was some function of time, and then eventually we'll write some functional equation and get that this is log. So then I can do conformal mapping from zero temperature to positive temperature. Then entropy as a function of time will become the same function of the different argument. V is my velocity. Remember, I had a picture here, and then I erase this. V is my velocity. Pi is pi, 314. This is temperature, sine. I want to, but on the other hand, I know that at positive temperature, thermal fluctuations much stronger than quantum fluctuations. So at positive temperature, I can't even see quantum fluctuation. This is pure classical, but classical, I know it's linear. So I write equation that this is linear function of time. So first of all, inside of this, I consider there is no x equal to 0. Time is large. So out of sine hyperbolic, I pick only one exponent. And then this is my entropy, that's function, unknown function of the argument, which is exponent of t, and I know that this function is linear function of t. So what kind of function this might be? Probably logarithm, because I take a logarithm of the exponent, I get linear function. That's a functional equation. So at zero temperature, entanglement entropy depends logarithmically on time. Okay. And then C is central charge, and then C is plus some constant will fix it momentarily. All right. So entanglement entropy. Now let's return to BFKL. So we want to describe the entropy spread from this photon along the chain. So C is equal to 1. This constant actually gives the units or time units. I mean, time is not measured in seconds inside this. M mass of the proton, so MT, the combination inside of this logarithm. All right. And this is explanation that we can calculate central charge from that beta ansatz. Now, this is, for me, this is the main result. This is the main result. So this is the entanglement entropy evolution in BFKL chain. Entanglement entropy, logarithmic. Nice. But then we can compare this with the paper of Harzeev-Levin and then structure function of the gluon. So Harzeev-Levin wrote long paper, N is the number of these color singlet dipoles. And this is a gluon structure function. So let me summarize in the next transparency how I apply this idea. So Harzeev-Levin wrote a generic paper. So let's apply this to GIS, different elastic scattering. So gluon structure function is equal to the number of those color singlet dipoles. And then this is as a function of time, this is X entropy. Entropy I just calculated. This is like 1/3 logarithm. So X of the logarithm, even I can calculate this. But then there is also a picture. We should keep in mind something. So this BFKL, everything what I explained happens for a very short period of time. The whole BFKL is like half a femtosecond. So exchange, and then hadronization starts, like quarks turn into jets. So we should have this in mind. So this Harzev-Levin, the idea was that when BFKL phase finish, then the proton come into the maximally entangled state, which is maximally mixed state. This is phase transition, and then hadronization starts. So they estimated that the time, it's called steering time, the time which takes before photon came, the proton was in the pure state. It was like resting in the ground state, nobody touched. So the entropy was 0. But at the phase transition, it's maximally mixed. So the time for the system, for the proton to go from 0 temperature to maximally mixed is MT 1 divided by X. All right, which also has some thermodynamic interpretation. So in here, this formula, I substitute instead of time 1 divided by X, I got this. And this sounds like a prediction. So we say that the gluon structure function for small x behaves 1 divided by X. This is Bjorken X. Bjorken X 1/3. So there is also some thermodynamic interpretation if anybody interested. One can look into the Hera data, and for small x, the data can be fed into the power. For the power, there's some range, and 1/3 seems to fit into the range, but close to the boundary. So I don't know, maybe later AIC will clarify. This is actually the end of the lecture. That's okay. Yeah.
Can you have a color octet dipoles? So gluons, instead of going 8 cross 8 goes to 1.
Maybe, I don't know. In my mind, this is high corrections. In my mind, this is
higher, say,
high corrections.
higher corrections, higher order corrections.
Of course, we neglect a lot of stuff of this. So we just guided by, the whole DFKL. I tried to read DFKL derivation. And it's like all your scriptures written in some dinosaur language, So, Kirchner has normal modern derivation.
So can I translate what you just said to the color singlet combination of gluons? It's going to be a lower mass. It's going to be a ground or more ground state than an octet.
I say that, yes, I rather agree. What do you want?
Can you comment further on this maximal entangled state time?
I can't even understand. Can you speak now then?
Yeah. So can you comment further on the maximally entangled state? How is that?
So maximally entangled state happens at the point of phase transition. Phase transition like BFKL exchange. Then there's like high down temperature, everything explodes, and hadronization starts. So the point of the phase transition is maximally entangled. It's kind of infinite temperature, but it's not really infinite. This is like high down. And then there's some estimate of how long BFKL lasted. And then somehow Harzev and Levin, they say this is the last one with X. It's not my derivation. Maybe that's another question. Anyway, this is a prediction. So no more questions, shall we conclude?
If there are no more questions, so let's thank Vladimir again.